So, welcome, Gülçin Dilderman, for the next talk in the PostgreSQL session for today, and it's about the evolution of fault tolerance in PostgreSQL.
Thanks. Hello, welcome. Firstly, I want to say sorry because I'm a bit sick and my throat is a bit hurting. Hopefully you will hear me. Do you hear me now? Yes. Okay, thank you. And as Christoph mentioned, I will talk about evolution of fault tolerance in PostgreSQL. I want to picture how we evolved in terms of dependability and fault tolerance by describing the features, the mechanisms, and all the features that is supporting and closely, tightly connected with fault tolerance. So who am I? I am working for Second Quadrant on Postgres and automation. And I also help for organizing Postgres events and do some talks. And also I'm doing my master's. Hopefully I will start writing my thesis soon. And that's it. You can find me from GitHub and Twitter, and you can add me from Skype if you want. Agenda that is, first we will talk about PostgreSQL database in general, but just a few, I mean. And then main mechanism for fault tolerance is WAL. Then we will try to describe what is transaction, what is commit, and what is checkpoint, and what do we have for replication in PostgreSQL, and what do we expect in Postgres 10 as well, and how the replication evolved from physical to synchronous replication, and then logical. And in the meantime, we will also cover timeline issues by failover, switchover, and PG rewind too. So first things are first, Postgres is robust, and by its own nature, it is already having ACID compliant, and we literally follow SQL compliant for SQL 2011, I guess. We try to keep the standards as standards. We don't want to change them so much. And also, transactions are the basic for all relational databases, but it is important for Postgres. So even if you don't run in transactions, PostgreSQL still treats every statement as transactions. And the thing that is transaction log, which we will talk about a lot in the talk, is WAL. We save all the statements in record in WAL files, and then use them for replication, for archiving, for all kind of reasons. And we have for detecting hardware defaults, you can use data block checksums. And there are a variety of diagnostic tools and lots of backup solutions. So you can be sure that if you configure your PostgreSQL properly and use all the environmental tools, you won't be facing with disastrous things in PostgreSQL. And this is very important. The last point, it has greater than 5 nines, and which means in fault tolerance is almost not achievable in almost all systems. So this is quite good number for synchronous replication, which we will talk if you configure and tune properly. There are a variety of levels of synchronization as well. We will talk in the talk. So what is WAL? The WAL consists of series of binary log files, and these are all under data directory of PostgreSQL. It's in pgxlog subdirectory. So all the changes that you do, you run some statements like insert, whatever, some command. They are all recorded in these data directories, data files, sorry. And just not only these ones, also indexes or when you run a vacuum. So all your changes are recorded in this transaction log, which is very important because when you want to recover from a crash or want to do point-in-time recovery, you will need these logs to know what happened, what changed. So this is your kind of diary of Postgres. And the safest, the thing that you should know, when a transaction is committed, it is not directly written to disk. So you should know that you can lose some data because there are some time between the commit and this commit goes to the disk. So we will talk about this as well. So when we say transaction, what we understand? There is this begin and commit that we all know. It is bundled. There are like intermediate steps that you run your queries, and when you commit it, it is like we call that transaction. So So, like I said, as I said before, in Postgres, everything is everything is considered as transaction, even if you don't write transaction as begin and commit, it is still is. There are isolations levels, 4 of them from SQL standard is coming. The important thing is here that we should know that PostgreSQL doesn't support dirty reads. What is dirty read? When I said that there are this begin and commit, and there are intermediate steps of that we don't, in PostgreSQL, the other concurrent transaction doesn't see these steps between. So let's say I updated something in the between, but the other transactions doing something with that table, they are not affected by these changes, because if there is some failure, it won't affect, we will roll back, and these changes not affect the other concurrent transactions. But there are some systems that dirty reads, that reading these intermediate steps, and which is not very good for for you and for your applications. So PostgreSQL doesn't support dirty read. I don't know how to point this, but yeah, dirty read. And the most heavy one is serializable. It is very hard to achieve, actually. So these are the transaction isolation levels in PostgreSQL. Okay. So what is checkpoint? We said that when there's a crash, we recover by replaying the walls, the logs that we wrote before. So how do we understand at which point we should replay these logs? There should be a point, that safe point, that we know that before that point, everything is written to disk. Because as I said, when you commit a transaction, it is not immediately flushed to disk. There is a time. So for checkpoint, in terms of checkpoint, that is the point that we can be sure. Let's say you had an issue or have a failure, and then there is one checkpoint. You can be sure that before that point, everything is flushed to the disk. So checkpoints is very important for that reason. You should tune your checkpoint settings. There are lots of variables in PostgreSQL.conf. It shouldn't be too frequent, or the time is important, because if you have a failure and you put a checkpoint some very long time ago, then you need to replay all the changes between that's written into WAL. So it should be, depending on your system, your load, your changes, and so that you should be sure that it will be averagely normal. It can be an immediate or scheduled checkpoint. Immediate means that you can write your command, for example, like checkpoint to command, and then you can immediately run this checkpoint. Or it can be scheduled, which means that you can also tune your PostgreSQL, and it is scheduled in some time, or it's how do you configure, and it is decided by PostgreSQL. So we talk about WAL. That was the files that we write in binary form. The changes are written to that files. In replication, what we do is, there is one, in classic replication, there is one master and one standby, and there are changes captured on master and then sent to standby over network. So here, what are we doing? There's master capturing the changes and writing to all files, and then sending to the standby, and it is replayed, and then now we have a maintainable copy of our system. That is basically replication, how it works. A copy of your system, basically your master system, and you have a copy on a remote server. That is generally PostgreSQL. PostgreSQL replication, we will go in details, but replication is this. And also in modern systems, reliability is important, and for redundancy reasons, we need to have replicas, right? So I don't want to go in details more here. And for an overview, we need to understand how we started. Things are not like this all the time, right? There was a history and lots of work behind it, lots of committers and lots of people contributing to this. But in the very beginning, around PostgreSQL 7, 2000 and 2005, there was a philosophy in PostgreSQL community that replication shouldn't be part of Postgres. And for that reason, there was long distance LONI, trigger-based solutions, because if you don't plan to do it in core, there will be some tools all around. What they were doing, we will talk about trigger-based replication, but we can consider them as logical, because they were not sending changes as physically, but there are triggers and tables we will talk. So it is considered as based on logical replication, trigger-based replication. PostgreSQL was focusing on single node fault tolerance. So if something happens, you can replay your wall and turn to a point that is safe for you. That was the initial fault tolerance in Postgres. And then by the time we get to replication, it was considered that if you have a cluster with more than one node, then replication is best for you. But then, how we solve the replication, how do we start to doing replication? As I said before, we took the wall and sent over network, and we have PostgreSQL replication 0.4, which is relatively new. We have logical decoding, which allows us to do logical replication. And in Postgres 10, it will be coming in this year, we will have logical streaming replication. And we will talk about the details a bit more. So that is the general view, how we were doing it, how state of the art is, it is still streaming replication. But now we will have logical streaming replication, and also we have logical decoding, so that we can use this as well. I will show how do we use logical decoding, so we are not restricted only for streaming replication. So physical replication. The picture is showing what I'm talking. So here we have master, and client runs the queries here, and then it is written to wall, and then wall is sent over network to the standby, and the recovery process on standby is replay the wall, and we have standby basically. And when we say physical replication, we should thought that we are sending these files in using some protocols like secure copy, TCP, rsync. And when we say streaming, when we are streaming here, what do we mean? That we have internal protocols for sending and receiving these files, which are like sender and receiver processes and wall internal protocol. Okay. When we consider that there is a replication, we assume that there is a way of doing standbys. Not everyone is needing to use hot standby. So there is in PostgreSQL, we can have warm standbys and hot standbys. So what is the difference between warm and hot? Consider that we have a base backup, that we have master and base backup, and we are feeding this base backup with wall files all the time. Then you have a replica. It is warm. If it's not active, it is ready, but it will be activated if it's needed. This is warm. But if it's already in the system and you are using it for read-only queries, and it is allowing to you query read-only while it is in archive recovery mode and file archiving mode, this is hot standby. The important thing is here, we can promote it without interruption. So your queries will continue to work, and here you don't have this chance because you need to wait for it to be activated. I think this is clear. While I was thinking about there is a big relation with wall and the replication, I realized that there is one parameter. It shows it really, you can sum up very easily. That is wall level. Wall level is the parameter that it determines how much information you will store for using your standbys, for which reasons, how do you want to use your replication, what is your main purpose to do for doing replication. The default and minimum one, obviously, is minimal. This is only for that in case of crash, you can recover with this level of information in your wall. Here, replica, this is slide is for 9.6. Before, in releases prior to 9.6, it was hot standby and archive, but they are mapped to replica now, but you can still use them. But what it does is you can do file-based archiving, you can run your read-only queries so that you have enough information about having this kind of replication. But then recently, as we talked, that there is logical decoding now. So if you specify logical, then you are allowing to use logical decoding, and then all the features comes with that. So it continues to look more to have logical replication in this level. And all the levels also has this previous levels information. So if you have logical in your wall level, then you have this and this, and if you are replica, you have minimal and so on. So this is, I think, very important, and you can just see easily what they do and what is suitable for. let's talk about failover and switchover a bit. As you can see in switchover, you have the control. Failover, sadly, you don't have. When your master dies, and you need to recover it so that you can accept the writes, otherwise you can't. If you do it by control, you basically stop your master and promote the standby. This is switchover. And this, you need to do something more. You need to do base backup or copying the files. And I will show that how we will fix failover situation in a better way with PG Rewind. So this picture you should remember if you want to know the difference between the terms. Switchover, you have the control. Failover, you don't. Timelines. I think timelines in PostgreSQL is a really important term to understand what is happening. Actually, why do we need this term and why do we use it? In every recovery process, after every recovery process, PostgreSQL issues a new timeline, so that you can know that the new timeline is not like overwriting the whole files that is written by the initial previous timeline. So that you need to diverge these timelines to overcome like switchover, like failover, crashes, and point-in-time recovery. So you need to be aware that we need different timelines to control this. And we will see this in details. So as you can see, in case of failover, this is our master's timeline, the first initial timeline. And this timeline increases here. So I assume that this failover is happening around here. And your master, these changes are not flashed to disk yet. So this standby, supposed to be new master, doesn't have these changes. So in this scenario, you will lose all these changes. You can't easily, the old master can't follow the new master because there's no way to send this to this. So what you need to do is like you promote and then do base backup and then continue. Because there are outstanding changes in the wall, and this timeline changes is showing that there is something messy. I mean, there is a failure. So it can't be replayed. But in case of switchover, as you remember, here is the case that we don't have the control. But in switchover, we have the control. So there are no outstanding changes. Basically, we stop this, and then we promote to new standby. But like I say, there is a new timeline issued here. And easily, the old master can become new master. The old master can become standby to follow the new master, which is the standby, like usual promotion without any loss. And what does PG Rewind is here? We are this tool is helping us after 9.5. There are still outstanding changes. It is more useful in the case of failover, for example. What does it do? It first checks the whole files in the old master. And the advantage of using PG Rewind and comparing to PG Base Backup or some other copying method is, in the usual way, you need to copy everything, even if they didn't change. So PG Rewind only looks for the changed ones. So let's say you have a very big database and you have like small, proportionally small changes. So you don't need to go through all the unchanged files, but this just checks and finds the changed files. So then you will have time. You will still lose this data. I will explain why you still lose this part. But at least your old master can follow the new master, so that you can do it in online. You don't have these failover situation now. So what was it doing? It was checking the whole files in the old, and then it was checking from the new standby. I mean, the old standby, but the new master. It is checking to going to a checkpoint, which I want to remind you, checkpoint was safe point. So, like, let's say there is this problem happens here, but you have checkpoint. You turn from this, you come to this checkpoint by just looking to this one, supposed to be new master, and now it's standby. You find this point and copy all the files from this one to this one, so that you kind of rewind the things and copy all the CLog files, configuration files, but not relation files. And then these walls are replaced by this master, which is not really detailedly replaced, but let's not go there. So that the important point is you can just continue. PG Rewind is help. So this is another improvement. I mean, before there was not this opportunity. Now we figure out a way to overcome that. Synchronous replication. Let's talk about this a bit. This one was greater than 5 nines available tenfold tolerance that I was talking. By default, Postgres do asynchronous replication, which means that we replicate whenever the standby is available, or how do we configure and so on. But we can force PostgreSQL do synchronous replication as well by configuring the synchronous commit parameter. Here, as you can see, that you can force that at least your data is written to at least 2 nodes before you send that it's okay, it's committed message to your application or your client. So you can be sure that it is safer. But when I say that what we lose here, we can lose a bit performance because I don't accept anything before I got the message that yes, it is safe. It is the place where you want it to be. So then you need to a bit wait for that. And another thing that maybe we can say that when you set synchronous replication, it doesn't mean that you only need to use synchronous replication, but it is for transaction-based. So you can set some transactions for synchronous, some of them asynchronous. So it is up to you. So that for some certain things, you want to keep them very well and secure, so that you can set for that transactions that's like synchronous, but some of them it can be still asynchronous. You can decide yourself, so that this trade-off between performance and durability is up to you. Just a bit. So which parameter is deciding this? Is synchronous commit. We will come to there, but before we go to synchronous commit and how it applies synchronization in PostgreSQL, I want to remind you how commit is processed in replication in general in PostgreSQL. We talk about it, but this picture is helpful, and I will use this template to explain synchronous commit as well. So here, this is our master, let's say, and this is our standby. We can think as upstream, downstream, doesn't matter. So here, when a client executes a commit, and this is written to WAL files, and then WAL sender is sending this to over network, and this WAL receiver takes it, and it's returned to standby's WAL, and it's replayed, and that's it basically. Then your commit is following this path basically. Okay, I think this template is helpful for basic idea. And let's talk about the synchronous commit. So here, this parameter is deciding if you will have a synchronous commit, synchronous replication or not. As you see, if it is off, we don't wait for the transaction record to be flushed to disk. It's off. And the second is a bit higher. This will go to higher level of synchronous replication. So the minimum was off, it was closed, and now it is local. What does it mean? That we can be sure that it is in local disk of the machine. So it's written here, but this level is stopping here. So when I say remote write, that I can be sure that I send this to the remote node, which is standby, but it is not flashed to disk, it is in memory operating system here. It is not here, but at least it is better than, the level of off and the level of local, it gone there and then said that, okay, it sent a message that is here. So this is remote write. The naming is a bit different because when I heard remote write, I was thinking it's written to disk, but it's not. On is the basic idea. Synchronous commit is on, which means that we do the synchronization by we send the changes now from this level and flush to the disk. Here we are now. And the extreme level, the top level is remote apply, that I push these changes that I recorded. These changes are visible on the database now, so it is replayed. So basically, the transaction is waiting for this event happens. So you can be very sure that it's even visible. This change is visible before that is turning to say a message that it's okay, that I did it. Okay, so this part that I think it's really important. That's why I want to show that in a graphical way so that we can be following the commit easily. Okay. So now we can talk. We talk. First, we started with valve mechanism, and then we say that how it is how it's used in replication, physical replication. In physical replication, you should think that it is row and block byte level. So all the changes needs to be replayed from the other side. So it is like a bit strict. You need to replay everything. You can't have differences between master and standby. But when we say logical replication, you can just put this keyword in your mind. It is more flexible. You can apply this to more complex topologies. You don't need to have the same major versions. And this is also an advantage that you can do. By using logical replication, you can upgrade between major releases and so on. So logical replication I think is the future of the fault tolerance and dependability in Postgres. But for some cases, not for all. Of course, streaming replication, physical streaming replication is still important, and it should be used for lots of cases as well. So that was a general intro for logical replication. There is two major approaches for logical replication. The one that we talk a bit in the history, that trigger-based replication, and then we will talk about logical encoding, and it is known as change set extraction in some other systems. So what do we do in trigger-based replication? Here, all the tables it is controlled by triggers, so all the changes are written to tables. You amplify the writes, so you write double times. The changes are written double times, and then also it amplifies the vol, of course, because then you have double amount of writes and double amount of vol. That is the caveat in this trigger-based replications. But it is, of course, predating the now logical replication, even the physical replication. But this is the caveat that you need to remember. It is like, it's okay, it is working. Sloan distance, Sloanee is doing this for years. But it has some disadvantages, increasing the amount of work needed to be done, and increasing the amount of the size of wall, and so on. Here, that's the main part that I want to show, and it will be in Postgres 10 as well. The talk will continue. Logical decoding, which is since 9.4. What does it do? Remember that there was a table that we had vol levels, and there was logical level. So when you use this information, what do? You extract the information from vol that you can use this information into logical changes. Now you don't think about that is like block and byte level, but you have logical changes in you now, and you can use it more for selective replication. You can just use it for some other topologies, and there is no write implication. This is referring to what? To trigger-based replication, because then you need to have everything double times. You need to write double times. So here, this is the advantage of logical decoding. There is no write implication, and there is another thing. When you use trigger-based replications, they are like using triggers as in the name, but the ordering is also another issue. You need to order the things that you copied, you write. But here, since we are using vol protocols, there is already in order. So your changes are in order, so you don't need to think about it in orderly. It is per row. So let's say you write an update for 100 rows, there will be 100 changes. And it doesn't decode DDL. And there is an SQL interface, which means you have functions. And it is using vol sender streaming interface. It also cares committed transactions, which means if you abort your transaction, this is not considered in logical replication. So based on logical decoding, this is very important because whatever I say here, it will be applied to logical replication and the extensions based on logical decoding that I will show you. So let's go. Okay. Here, what I can say that is, here, as you can see, in the physical streaming replication, we were again using this vol sender and vol apply processes. We still use the same protocol, but we do logical replication now. And it is currently available as an extensions. PG logical and PostgreSQL. We will have a small talk about them as well. And obviously, it is better performant than trigger-based replications, which is the reasons that I listed before. And it is built on top of logical decoding. So that is the view. And it is also allowing synchronous commit. Why? Because we still have this same protocol for ball and stuff. So you can still do synchronous replication. So what is PG logical? Since we have the logical decoding in Postgres now, we can have extensions and can do logical replication. This is an extension for logical streaming replication, and it is available after logical decoding, basically 9.4. And it is optional synchronous. Why? Because logical decoding is allowing us, in the previous slide we saw it, we configure it via functions, and you can do row filtering and column filtering. That is the thing. You can do selective replication. Now your limitations are less. You are more flexible than the physical replication, and it is you can use it for many reasons, for your BIs, and you can have different data sets in different platforms and everything. So it is better in these use cases. And the thing is that you can do major release upgrades, because then in the physical replication we are limited to use same version, but here we are not limited to that. We can use from 9.4 to 9.6, for example, for upgrades. So this is PG logical. This is the good news, good slide. PostgreSQL 10. In PostgreSQL 10, we will have basic built-in logical replication in core natively. And of course, it is built on logical decoding. Again, you see the same sentence, which is optionally synchronous, because what? We have this now. We can do optionally synchronous. And the difference is from PG logical and Postgres 10. In PG logical, you have functions to configure the PG logical and logical replication. But here, you are not. It's in core. You can use DDL. So you will create publication and subscription. There will be publisher and subscriber nodes. And it is based on PG logical. So it implements some features of PG logical, but it will improve by time, because there are like lots of actually stuff that we waited to be in core. And different implementations, of course, but same logic applies. So PostgreSQL 10 and PostgreSQL. This project was used for, still is used for feeding logical replication development in PostgreSQL. And this is multi-master. When we talk about replication, there's also a difference between like a multi-master. If you have more than one master, it is obviously multi-master system, and then the traditional replication is like master standby. So BDR allows you to have multi-master and asynchronous. That is important. And the main aim was for BDR project that you can have globally distributed cluster. So you can actually distribute your load in your local systems. Let's say you have 2 servers in America, 2 servers in some other country, 2 servers in Ireland, let's say. If you distribute the load in the masters, because it is asynchronous, so you don't need to wait for writing. You write, and then you divide the load for locally, and then they will get synchronous eventually. So it is eventually consistent, cluster-wise, so that you can have globally distributed clusters. This is all thanks to the logical decoding and the projects behind. So, and you can think that, I mean, if I write the same table, if some other people write the same table, what will happen in all cases of multi-master solutions? Conflict. So there are lots of ways of handling these conflicts. And in case of BDR, it is optimistic. This means that after commit, it will be settled, this conflict detection, and then automatically this conflict resolution will happen. I think for BDR, it is last committed one wins. So this is important. When we say asynchronous, doesn't prevent concurrent writes. That was the reason, actually. If we prevent the concurrent writes, we can't have this locally distributed latency, right? We are trying to solve writes locally, so that we don't need to wait for it. Usually when we do traditional replication, what do? Mostly we are scaling the reads. But for scaling the writes and distributing the load, we need multi-masters, if it's your case is like available for this kind of architecture. So this is PDR, is again on logical decoding, and that features that is allowed for us. For conclusion, what can we say? That we can see that it is a long way that we came, and we will still go lots of way. And there is either out-of-box solutions. What is that? But what I mean, we have a wall mechanism, which is like used for all the replication that we talk, all the decoding, logical decoding. So we have wall, we have replication, different types of replication now. It is getting better, and like more like variety. And then also PostgreSQL allows us to use extensions so that you can write your own plugins, and you can use it. Actually, logical decoding has this C output plugin so that you can write your plugins, API, so that you can write your plugins for like cache validation, for example, or like integrating with Kafka or some other tool. So you have the control, which means that fault tolerance and dependability is getting better and better. And as I wanted to show that we come a very long way, and it is going better for me. And as a last point, it's that I focused logical replication in core will be the better and next leap of in terms of fault tolerance and dependability in Postgres. So I guess that's it. Thank you.
Oh, there's a visitor coming.
So great. Oh my.
Okay, we have plenty of time for questions. So please wait for the microphone.
I will explain later. Can't. Thank you.
Thank you.
So questions? Do we have?
Yeah, hello, over here.
Yeah.
So I just want to check because maybe I misunderstood, but it seems to me that when you're talking about logical decoding, what you're replicating is just the statements instead of the changes to the data files.
Yes.
Okay. So
not statement-based, but not data files. Yes.
beg your pardon?
I mean, it is not binary changes that we write, and it is what was it? Row-based? Yes, row-based. So it's not statement-based, but row-based. For example, when you write an update, which is affecting like 100 rows, there will be 100 changes. It's row-based, but not directly statement-based.
Okay, but what will happen if you have like some information that will be different depending on which server? Like if you send an insert that has a timestamp,
Okay.
and maybe the time on the two servers will be different. Will it still work? Will it just take the time that was inserted on the master and use that same time on the replicas?
I don't know the details actually, and there is the author of logical replication here. He can maybe respond. I don't know where he is. I don't know. I think it will replicate anyways, so it doesn't mind the timestamp changes.
So it actually replicates or decodes the changes that happened to the data. So if you insert timestamp or random or something like that, it evaluates it, writes to the table or and val, and then what was written is decoded to the stream.
So it does what he responded. It doesn't care about the timestamp, but it already decodes the changes that you write to data.
Okay.
It doesn't do this.
There was another question around here.
I see one hand there. Here as well.
Okay.
Also here.
Cool. So you mentioned that the logical replication also supports synchronous commit to one of the secondaries. Does that mean that there is some sort of shared part of the protocol between the old school disk-based replication and the logical stuff? Or does the logical decoder provide some way of blocking commit on the primary in order so that you don't acknowledge to a client until it's on two nodes?
I think from my understanding it is using the traditional way because we have this wall and we are using these facilities, it's coming from this wall process. So that's what I understand. And
Okay.
if I'm incorrect, yeah. I mean, it doesn't have the extra thing depending on logical replication, but it is using the same traditional way.
Okay.
Oh, you.
Here and that was here.
So, so you mentioned that the logical is like another level to wall writing, like write-ahead log level.
Yes.
So, but there is also logical extraction. So, do you actually like try to decode whatever was written like in write-ahead, or you actually write another type of
Yes,
write-ahead log?
yes, you save another type of information.
Okay, so what the extraction then stands for? Like, what does it extract? Well, it's just a read.
It has more information.
I guess I can answer this better with.
Instead.
So it actually decodes the data that you would write normally. The logical level just adds some additional information that you need. For example, if you do update, it stores the data about the previous row. So because you need to actually somehow identify the previous row, so it puts it there. With normal update, you would only get data for the new row, but with the logical, you need the old one. But the decoding then decodes the binary data from the val to actual changes for the API.
Okay, so it has more data.
So,
Here.
Hi, thank you. So going back, my question, someone's already asked half of it. So the logical replication, as you said, if you've got like a million row update, it will break down into a million one line update statements. I've seen that with other products, other database engines, and it can cause the replica to lag quite horribly.
Mm-hmm.
Is there any sort of clever logic for handling those scenarios with logical replication? This was quite a while back when I saw that problem. I'm starting to use Postgres more and more, and I'm just worried that I'm going to see that again from that problem I saw 5 years ago all the time with it wasn't a Postgres, but it was logical replication, and it was exactly that scenario. A million row update gets broken down into a million single update statements, which takes a long time to process.
I'm not logical replication developer, but what I know is this lag is almost all the time the problem for any kind of scenario. So I don't know how they handle it in production use cases, but what I know is it is, for example, better perform. There is the performance reports actually from my colleague Tomasz, and he wrote in our blog, for company blog, that he kind of compared with replication in 9.4, replication in 9.6, physical replication and logical replication in use, so with benchmarks and so on. So it doesn't have this huge gap of performance that I see from the graphics. So I don't know how they handle it, how they manage it, doing it better, but there is they're working all right. And it's the obvious thing that from the theory that we can see, at least that is in the presentations, compared to trigger-based ones, they are really good performance. But they don't have this huge gap of performance that's coming from physical or logical. So it is, it's in use and it's used. Because since 9.4, it has lots of time for people to try and use it. But in core, that we don't know yet. I mean, we know that it will be in part of Postgres 10, but we will see how it will work. And I don't have a performance test for 10.
I have a question about the wall here.
Yeah.
For how long is data stored in the wall? Let's say you have a table with a limited number of rows, but with very regular updates. Would the wall grow indefinitely based on those updates, or is all data discarded at some point in time? How is that handled?
You need to decide how long you want to keep your walls. So it is depending on your configuration, basically. You can keep it unlimited time, then you will run out of disk space. But you need to be sure about your dynamics. How much do you do checkpoints? How do you replicate? And so you need to configure it.
Okay.
If I understand correctly the question.
Yes. And is the data also released back to the operating system when it's been discarded, or does it keep the old records allocated but empty for future use?
It is beyond my explanation, I guess. I don't know how it works very... does anyone explain this better?
You might have to repeat it, but the gist of it with wall is
Here, you can use mine.
Okay. Yeah, so I mean, the wall is going to stay around for as long as you have it set up to. There's some different commands that can be used to do kind of archive cleanup and also archiving. When you do archive wall through with Postgres, it's going to release that once it's done. But if you're doing logical decoding with it, then you need that wall stream for as long as you have a ongoing transaction or throughout a given checkpoint at least. Anyway, you're going to need that anyway. So it's not really kept around. Eventually, it does get recycled. So inside of Postgres, as long as your archive command is working properly, assuming you're using an archive command. If you're not, then it shouldn't actually need to keep it around for longer than a given transaction, is my understanding. Okay?
Thank you.
I just got a question. As far as I understood, the data files between minor versions of Postgres are compatible. Where is the benefit of logical replication between minor versions? Or is
for
that
minor versions, it's already easy to do upgrades. That's why I emphasize major versions, because recently it is harder. There are solutions to do this PG upgrade, and you can still do that, but it is better because you don't need to use the same major version. That was I'm meaning. So for minor version, you can use it, of course, but it's not needed. In my
okay.
point.
Thanks.
Yeah, you're welcome.
Hello.
Hello.
With streaming replication, synchronous replication, and replication sorts, we have a new failure mode, which we encourage sometimes. When you have a slave which for some reason becomes unresponsive, your WoW partition is filled, and after some time your master is also going down. Do you have some solutions besides monitoring for dealing with such situations?
You need to, the basic thing maybe I can say that you need to monitor your replication lag. So you need to be aware of before it got uncontrollable. So you need to know that what is acceptable for you in terms of lag, I mean in bytes or in time. So then you don't need to be like, oh, okay, it's like everything is filled and it's like not catching at all, and it's like it is like too much lag, so you don't need, you need to do base backup or something, start over. So before that, there are like lots of monitoring tools that I don't know actually externally, but you can find it. If you are a reader of Planet PostgreSQL, all the company blogs are going there, so you can find their tools. Also, there is Check Postgres, which is mostly used, I guess, the scripts, so that you can just check and implement in your monitoring. Replication, like you should definitely check.
Okay.
There is one question here.
What is the difference between streaming and non-streaming replications from the point of implementation? Why streaming replication is more efficient, and why Postgres protocol, internal protocol, is better than, for example, rsync or something like that?
I don't know actually how the implementation in the code, because I'm not the developer, but what I know is that you can use this, if you want to send your files, you can send it, because there's this data directory, you can send your files with any kind of protocol. But if you use our internal vault sender and receiver protocols, it possibly has more optimization, it is more like you don't need to control it over, so it is streaming all the time, you don't need to ship your files. That is what I understand. And Steven wants to say something more. Yeah. So why is better?
If you're sending files, it's sent in 16 megabytes chunks, so you're always lagging 16 megabytes behind. And if you're streaming, you're getting the data in real time.
So instead of like shipping them, like bytes, you'll just stream it. Yes, yes.
Yeah. The other thing is rsync is single-threaded.
Yeah. Also, this is multiple threads.
Thank you.
There is one question here.
Oh, okay.
I don't know if you... Ah, sorry.
Yes,
I thought
also a
first
question.
off. Sorry.
No problem. If I choose a logical replication, does it mean that I have twice all the information? So I will get the size of the world will be more?
It will be more, but I don't. I asked this question before. It won't be double. There's not that huge difference.
Not
if
the
I
double,
know,
but
yeah, right. It is. Yeah, there is something. I mean, not all the information is in the wall because it has also other stuff that's done inside. But your wall is not going double.
Okay.
This double thing, maybe you remember from the trigger-based ones, because they were writing up double time, so double writes coming from there, but not in logical replication sense of this.
Okay. Thank you.
You're welcome. There was one more.
Question for you. You said wall is single-threaded. Okay. Sorry, you said wall is single-threaded and streaming and multi-threaded.
No, sorry, it's not. Sorry, microphone. So no, I didn't mean to imply that what we have today is multi-threaded. I was just pointing out that that's one of the issues with rsync. It is something that we're looking at doing in terms of being able to support parallel archiving of WAL. It's not there yet, but I've had a discussion with Magnus about it that I think is looking promising. So in the future, the idea is that we'll be able to do parallel archiving. It's just not, no. So right now, no. But you can't with rsync at all. So.
Okay, maybe one last question.
Yeah.
So the question is on if you have application and long transactions, do you log this before you commit, so we actually can stream things while the transaction is, or replicate while the transaction is running, or is the thing just going into the log when the transaction is finished?
After commit, I know if I know correctly.
Okay.
Yeah.
So if you do like a large, or that's a follow-up question with alter table type of commands, will I have to complete on the master before it actually starts on the slave, or how do? Okay.
Okay, we have a few minutes left, but I think we had plenty of questions, so.
Maybe
okay.
One last one. 2 minutes.
On the change set extraction, it said that DDL wasn't supported. Are there any implications with respect to schema changes?
Sorry, I didn't quite get it, I guess. There was.
Well,
DDL, yeah.
So, on your slide
Yes.
with the change set extraction, it said that DDL statements weren't supported in the extraction. So, does that have any implication in terms of your master and slave when you're doing schema changes?
What kind of implication can be seen actually?
Well, the short answer is that things are getting complicated.
Yes. Yeah, he's asking like in case of alter or something. Yeah.
You need to sync everything and then do the changes at all places at once. And I think the idea is that the Postgres 10 will get the DDL replication as well, but it's not there yet. So PG Logical is far ahead than what's in Postgres core, but it's it's not in there yet.
Yeah, so it's
yeah,
really
when it's when it's in when it's in core, it won't be a problem.
Okay, so thank you again.
Thank you.
Okay, and the next talk will be starting in 10 minutes at 3 o'clock.
I'm running multi-master with this.